a PowerPoint presentation,
Yeah.
a special scenario. Music.
That's funny.
Okay. Start from here. Now where's your film? Physics exam. Hi Jeffrey. Why are you so serious looking?
What's that? Oh, it's
Okay.
waiting to go.
Oh,
Ready?
okay.
Equilibrium, oxidation reduction. Sounds good.
Okay. So the topic begins with, again, the K. So the usual way, you write it. So when you look up, when you need the value, then you look up the table, right? So the K is a constant, equilibrium constant. Now, you can also calculate from the E-naught table. So what you need to do will be simply identify the two half reactions. Once you get the two half reactions, then you can just plug in this formula. So memorize for this formula. Now the N, now you have two half, hey Misty. You have two half reactions, right? So the N is which one? It turns out that the N is a common number of electrons. So the N comes from the complete reaction, the equal number of electron transfer. So we will talk more about the N because it appears a little odd here. You need more understanding of it. Okay? Oh, you cannot see it. No, how to make the butterfly. I used to be able to make it well. Okay? So this is the formula. Yeah, Jeffrey, sorry.
To identify half reaction, we'll just see in the just express like electrons in the
Right.
balanced equation. That's how we'll be.
For the half reaction, you will see the number of electrons.
And that's what.
Then you balance the number of electrons from the two half reactions. And that balance number goes to here. I will give you examples.
So then a
for
full,
that.
a full reaction is there's a complete transfer of electrons and no excess.
Right, exactly. Yeah, because this formula is for this complete reaction. So the equilibrium K for the complete reaction is not for the half reaction. And therefore, this N will go for the electron transfer in the complete reaction. Okay? So this is the formula you're going to memorize for certain exam questions. So memorize a formula, you need to feel confident, right? To use the formula. So we will prove this formula next. Okay, here comes the proof. So, practically speaking, you have two chemicals, right? So one of the chemicals is reduced form, and other one must be in oxidized form for complete reaction. So you put the two chemicals in. Okay, so here we are talking about direct mixing. Once it's direct mixing, the electron transfer is complete instantly. Okay, and it's at equilibrium. So one can envision as if the two chemicals electron transfer, right? But then the transfer is complete instantly. So what it amounts to when you look at the potential for each chemical, then the difference will be 0. So memorize this. Whenever it's at equilibrium, the delta E is 0. So in case this is a cell, okay, a galvanic cell, then this represents a dead battery at equilibrium, right? Because you have a experimental potential here, you have an experimental potential here, the two is balanced for, and therefore there's no electron transfer, so you get a dead battery. Okay, so for direct mixing, it's always a dead battery. It better be, otherwise you stick your finger in, you get an electrical shock, right? So keep this in mind. So at equilibrium, the delta E is equal to 0 between the two. So now the proof, when the difference between the two potential equal to 0, then, right, the difference between the two is equal to 0. Okay, so cold and uncold, if you call this as a galvanic cell electron transfer, then it's a dead battery. Okay, if you write this Nernst equation, right, because this is 0, then EA is equal to EB, right? The two experimental potential being equal. So that is the key thing for this write-up. So it is an experimental potential. So you write a Nernst equation to describe the equivalent, extrapolating to the E naught, then you would write it like this. So EA is equal to this Nernst equation, and EB is equal to this Nernst equation. So set the two to be equal. Okay? So any question with this point?
Well, you said EA equals that right there?
Right. So because 0 is equal to this, so you put EB to the left, then the two being equal, right? So that's what it is. So EA is equal to EB. So this is experimental, right? You did the experiment. So this experimental potential equivalent to the extrapolation to E naught in a Nernst equation and plug in the experimental quantity.
When you say there's an instantaneous transfer, does that mean that there's just an infinitesimal amount of time that can't be measured?
That's correct. Yeah. So once you mix, then it's done.
But the fraction of time is so small that you can't.
That's right. That's right. Yeah. Because you are referring to the equilibrium constant. So it is at equilibrium. So you mix it until it's stable. So as you are mixing, then there will be electron transfer. Yeah.
Are there different rates of transfer for different species?
Right. Yes. Yeah. Yeah. Even for direct mixing, there will be different rates of reaction, right? So as evident by looking at color change in some reactions. You see color get more darker and darker until it stabilizes.
And is that related to its reduction potential?
The
quickness of it? Or
well, it depends on the chemicals. We will talk about that, later. The rate of reaction is based on other factors. Yeah. But what is reached equilibrium, then the condition is this. Okay? Because we are doing equilibrium constant. Another question? Okay, so continue with the proof, then just a matter of mathematics. Okay, so you do arrangement. So you put the E naught to the same side, to the left side, and extract the common factor, which is 0.059 over n. Then you're going to have the log like that. Okay. Then for further algebra, then you will get a situation like this. So the minus becomes a plus. So once a change, then the log ratio flip upside down. Okay? So now you have a plus in between, then you can combine and take the log. So it is going to be B ox multiply A ox over B red over A ox, and therefore that is the K, right? Previously K is equal to that multiply that over this multiply that, and therefore that represents the K. Okay, so that becomes a log K. Any question with that? You see it, right? Because this is a plus, you get rid of this plus, this is log, and therefore, combine the two, then it's going to be multiplied. And that is the k. Okay, so the formula is proven to be true. So, so from now on, you can use that formula in confidence. Any question on that?
So why did you
And memorize for.
Why did you switch it from minus to plus?
For the purpose of making it k, the definition for k, because the formula is for calculating the k. Okay, and these two are table values. So it's on purpose or for a purpose. Okay, so homework. Picture of the homework.
Alrighty.